Let's wait for 20 seconds. Will you turn off your...
I'll do it again.
So let's start. So we are very happy to have Gleb Aminov from Stony, Brook, who will tell us about the language of black holes.
Thank you very much. I'd like to thank the organizers and Stasia for giving me the opportunity to speak here. It's very exciting, just to me. So today we're going to discuss analytic approaches to black hole quasi-normal modes, and this is the other way of saying it, learning the languages of black holes. So first we're going to answer the question of why are we interested in quasi-normal modes, and even call them I call them here language. Then we'll give a broad definition of what a QNM is, and its relation to the gravitational wave astronomy. And then I will introduce two different approaches, analytic approaches to compute the quasi-normal modes. And finally, I'll finish up with some summary of current and maybe future results. Yeah, this is so the talk is based on two papers of Mike Arfas and I, and one ongoing work with a PhD student Paul here, in the second paper, and the other links are the materials and pictures I used for the presentation. So first, we'll answer the question why we're interested in quasi-normal modes. Is that we know we have, at least I can tell right now, about 3 detectors of gravitational waves. The most famous are LIGO and Virgo interferometers. LIGO even has, so both of them are based on Michelson interferometer. They are large-scale Michelson interferometers, and LIGO even has 2 of them. So 2 interferometers in 2 different places, one in Livingston, the other one I don't remember actually, and then Virgo also is in Europe somewhere. The third one is in Japan, and it's like called Kamiokande gravitational wave detector. It started, it shut down because of COVID, and then right now it's supposed to be running. I don't know if they will have any results. So this one is the first observation, gravitational wave vibration. Probably we've all seen this. I'm just showing this for so that we know what we're talking about. So we're talking about, this is the small line here is a numerical relativity, and this is a reconstructed, basically reconstructed signal from the measure from the experiment of LIGO, and it was received in September 14, 2015. And what we see here is that there is like different phases, at least 3 phases we can see here. First phase is when the 2 black holes or any other bodies are in spiraling. And then like they coming closer, and then like spiraling in relation to each other. Then they're gonna be merging, which is gonna create a stronger signal. And after they almost done merging, we have the creation of a black hole if the masses are enough, and this black hole is gonna vibrate at some frequencies, and these frequencies are going to be damped. This is called the ring down mode, and this is where this phase is dominated by quasi-normal frequencies, because most of the properties of the black hole are already like the black hole is settled, and we expect that it's gonna just cool down, or leave the excited state and emit some oscillations. So there's damped oscillations. What's the problem with the current? Not the problem, but like what's the thing with this current experiments? They're like microsound interferometers, as I told you before, and the arms are like 4 kilometers for LIGO and 3 kilometers for Ergo, and they cannot really distinguish between different frequencies in the ring down phase. They can measure other frequencies, but the QNMs are not in their range. And so in the future, we expect that there's going to be another experiment, even more, I don't know, this looks like pretty cool. There's going to be they're planning to put 3 satellites on the Earth-like orbit around the sun, and the arms, like 2 satellites are going to act like mirrors, and one master one is going to be receiver, and is going to be like sending the signal, the laser, and receiving it. And so the arms here are going to be like 2.5 kilometers. At least this was like the ELISA, the latest 2017 version is gonna have, supposedly gonna have 2.5 million kilometers arms. And so those, if this experiment works, we will be able to really distinguish the frequencies and try to understand if the general relativity or our understanding of black holes is up to, is on par with nature, or we're missing something. And so that's why we want to study quasi-normal modes, and especially analytically. This will allow us analytically because obviously everything is going to be like any physical object, like bell or string, they're going to vibrate, if possible at the lowest frequency, but there's going to be overtones and there's going to be like mixing of signals. And so having higher order corrections to linear perturbation of gravity, which are QNMs, are just linear perturbations to the black hole solution, having higher order corrections is very important. And to get to higher order corrections, you need to have analytics for the first order. You better have to, at least. So now we just, what is the quasi-normal modes in the most broad terms? To get to quasi-normal modes or to define them, we just need to have like 2 things. We just need to have an ODE. Here is that we have second order ODE and the boundary conditions and 2 points. So it's like a 2-point spectral problem or whatever. And those are, I'm separating them because it's going to be useful for me in the future. So yeah, it's just ODE with the boundary conditions. And so today we're going to discuss mostly Schwarzschild black holes in 4 dimensions, and they can be put into different backgrounds, like Minkowski flat, so flat background, or de Sitter or anti-de Sitter. Obviously, we will start with ordinary black holes and in Schwarzschild solution. Kerr solutions, we can also study them, and we did. It's just a little bit more complicated because there is like 2 equations. There's not one equation that describes the radial part of the perturbation. There is equation that describes angular part too. So for the Schwarzschild, it's only about the radial part. So where should I write? Maybe here. So this equation is basically, we have the perturbation to our gravity action, just Hilbert-Einstein action, and we are going to have our perturbation, which is going to be a function. It can be like a scalar or a vector or tensor perturbation, and we're going to obviously expand it in the spherical harmonics, because we have a spherically symmetric problem for Schwarzschild. And then this part we know, this part we don't know, and we're gonna obviously look at waves. The time dependence is gonna be wave-like, and there is some unknown function. And this is basically, and 1 over r here, sorry. And so this is basically the part that we're gonna write our equation on, and this ODE is called Reggie-Wheeler equation on phi of r. Here we have obviously this part coming from the Schwarzschild solution, and the effective potential here. Correct me if I do some misprints. That's okay. And so I'll explain here. We have obviously L coming from spherical harmonics, and S is it's not coming from spherical harmonics. It's coming from 3 different things. We can either consider a scalar perturbation to our action, or we can consider a vector, or we can consider a tensor. Tensor meaning gravitational waves. So all of these 3 kinds of perturbations are described by the same equation, and obviously S is 0, 1, 2, scalar, vector, tensor. So for the purposes of measuring anything by detectors, we're going to be interested in S equals 2. And obviously we need the boundary conditions. Those are, now we know, plane waves in R star. If you look at this potential V here, we'll see that R goes to, when R goes to 2m, obviously it's a 0 because of f of r, and also when R goes to infinity, this is also 0. It's dominated by 1 over r squared, 1 r cubed. So the solution is going to be a plane wave in R star, which is just this, right? And so that's why we have, those are plane waves I omega r star or plus I omega r star. And you're asking that our oscillation, we don't have any incoming energy into the system, and so we have only waves falling under the horizon and only waves leaving at infinity. There's nothing coming in at infinity, so this creates for us a good problem for we can find discrete solution to that problem. It's like setting Dirichlet boundary conditions for the string or any other example. The only difference with strings or other examples of spectrums is that here we're losing energy into the horizon and into the infinity. So the solutions are discrete frequencies, and they're complex because it's damped oscillations. Damped oscillations.
Existence is not guaranteed, right?
Oh, that's it's not guaranteed. But I mean, we can expect, as I said, like thinking of like black holes as any other object. If it's like vibrate, like you vibrate it and you ask for proper boundary conditions, I would say if you ask for proper boundary conditions, I would expect them to have discrete. But yeah, I can say that it's guaranteed.
Wait, you can say it is or it isn't?
Yeah, I can't. I mean, I'm not. Yeah, I'm not studying if like if it's a.
Because I think there are examples
Distance.
which are probably not very physical, but if you just mess with this F at the horizon, then there are examples where there are no solutions.
Or discrete frequencies, yeah?
I think none, or at least, yeah, I believe there are examples where there are no solutions at all.
That's interesting, yeah. But like we'll see that the examples of like easier examples of ADS, they're in some sense easier, and ADS is a box, more or less. And then there is just obvious that you're gonna have some frequencies in a box and they're gonna fall in. Obviously, like there we'll see that the ADS without a black hole is gonna have discrete frequencies like a box. And then if you put Dirichlet boundary and then you add a small black hole, it's gonna create an imaginary part for the frequency. So yeah, some examples. And this is basically related to ADS by taking the lambda to 0 limit. So
Sorry.
yeah.
Also, you mentioned that in the more realistic care case, like you actually get coupled partial differential equations, or
Yeah, you solve one you solve for ASLM. So because it's not
I guess,
anymore.
yeah, can you reduce it down to an ODE eventually, or
Yeah. You again solving two ODEs, one for so-called ASLM you solve for that, and then you substitute the solution into a very similar equation as we have for Schwarzschild. That's why I'm saying it's like, yeah, everything I'm speaking about is applicable, but not to the angular, but not to the angular part of the problem, but to the radial. But the angular part is very nicely solved in terms of instantons that I'm gonna discuss too, analytically. So analytically, I mean, you expand in small j, which can be like a rotation parameter, and you get analytical answers. Okay, let's move on. I moved in the wrong direction. Sorry. So this is a very simple example. I didn't have time to put a lot of oscillations in this potential well, but sorry. So our main idea is that this problem is the same as doing quantum mechanics. In quantum mechanics, you divide the space into regions, 1 region, 2 region, 3, and then apply boundary conditions. For example, you have an infinite well, you have the wave function should be 0 at the boundaries of the well, and you solve it and everything's fine. Or more, or harder problem like here where you have 3 regions where you need to solve things. So that's a good simple example of what we're gonna do. First approach, yes, is
quantum mechanics. When you have a small well, you're always guaranteed to have a quasi-normal.
Yeah, well, I'm saying more like, I'm not saying our potentials are going to be like wells. But no, they're not. I'm not saying anything. They're not wells. It's just an example. Our potential or whatever we're solving is not necessary. It sometimes has a well if you write effective potential. Sometimes doesn't. It's like it's more complicated. But I'm just saying when you boil it down, it's just okay. When I'm solving the quantum mechanical problem, I need to have regions, and then I need to ask for the continuity of a wave function and its derivative, and that's it. Easy. So again, I'm doing it in the wrong direction. So for Zyberg-Witten curves, the same idea is that we have the quantum curve here is just a Hamiltonian equation or stationary Schrödinger equation, and the curve comes from the h bar to 0 limit, where if you go to the quasi-classical approximation, you'll see that there's some kind of a complex curve there, and there's studies like called Zyberg-Witten curve. And so talking quantum, we just have a Hamiltonian that acts on the wave function, and you have a spectral problem. And the thing is that we can just rewrite one equation ODE in terms of another ODE, and it turns out that there's 3 cases that they're considering today: Schwarzschild and de Sitter, Schwarzschild de Sitter. They're the same equations as like these curves for 3 or 4 flavors. And I actually want to write the equation, but let's keep it for now. There, I can write down the equation for the curve if you're interested. Equation, I mean the Hamiltonian, and the boundary condition turns out to be the same. We'll see that that's somewhat of a coincidence, but not fully coincidence, but that's good. And we'll see that in the anti-de Sitter case, the boundary conditions are different, even though the equation is the same, and this will change the story a little bit.
Special to 4, or does it generalize to other dimensions?
This is for dimensions.
In other generalized to higher, let's say.
Yeah, 5D. There was a paper by Alba and other co-authors. They did 5D, ADS, I think. There's like you're gonna figure it out. It's just like so. This part is just writing one differential equation in terms of the other, and the main thing I'm gonna talk about. The main thing you're looking at is singularities. Number of regular singularities, number of irregular singularities, and as soon as you see that the singularity structure of the equation is the same, you can basically match one to another almost always. Because yeah, the solutions are gonna be like depending on the singularities, you're gonna have like certain specific functions. For example, hypergeometric function is a solution to certain number of singularities, and then there's generalizations. Okay, so what do we want from Zyberg-Witten theory is that we are solving the equation, and we want the quantization condition, which in terms of Zyberg-Witten theory, this gives the energy levels of the system. And what is this quantization condition? It's called a B period, because you'll have like C here, you'll have X, and you'll have a turning point. turning points where the energy meets the potential, if you think classically. And then the wave function, your particle is in the potential well, it bounces around. There's a wave function when it goes around this turning points. And so basically this B period is the phase of the wave function if you write it in this WKB approximation. So this phase here that, do we have a 9? Yes, we have a 9. This phase here that wave function develops when you go around one period of oscillation should be 2 pi I, right? So there's I over h here, multiplied by this is 2 pi n, means that the phase went back, and our wave function is actually continuous in the intersection of two regions. That's exactly the same thing. Here is just written in this way because if you do WKB, you're gonna look at the phase of the wave function and you can talk about it. There is Nekrasov language probably, I don't know what language does he use, but when you do WKB and expand an H bar, that's what you get. You're basically solving two regions and asking for the wave function to be continuous. And the thing is, why we need Nekrasov-Stashvili function here is because it resums all the H bar corrections. H bar expansion is not really convergent, and the Nekrasov-Stashvili function allows you to just put H bar to 1 and don't worry about it. It's just an expansion in the cutoff parameter lambda here. So in this theory, it's related. Everything here is related to the supersymmetric low energy effective theory, and there is a cutoff there. Let's say lambda.
So what is H bar related to in the black hole problem?
H bar is just 1 in the black hole. It's like whatever you have in the derivative, right? It's just 1. I mean, it's a dictionary, so you can play with the dictionary, but basically it should be 1. And we are going to use 1. So, but this thing is not enough. So this B period, you have the function, you plug it in, you do everything. If the boundary conditions don't coincide on this between the quantum mechanics part and gravity part, this is not enough. That's what we're going to learn. This comes. So now I'm going to point out what are the some of the what is the room for improvement in this approach. Is that in some sense this supersymmetric language is foreign to black holes because it's written in terms of flat moduli A, and this is a complicated function of E, energy. So we have in our spectral problem energy on the right hand side, right? We have H psi equals E psi, and this is the parameter that we can easily write in terms of black hole. It's written here. Black hole parameters. Omega is m squared omega squared is the quasi-normal frequency. L is the quantum number. And you need to invert. You need to write A in terms of omega. So this is a complicated function that you need to invert, which is doable. That's fine. Another issue that we want to solve is that you can't actually really have small omega expansion. This supersymmetric expansion in lambda, even though lambda is actually proportional to omega, and to get answers, you basically doing perturbation in cutoff. In the dictionary, lambda is just proportional to omega, but it's not. You cannot. It's not an expansion of small omega. It's an expansion of small lambda, and I will try to show why. It's not an expansion of small omega. So you write everything here, like the instanton part, for example, I wrote the first correction and then so on. It's written in terms of lambda times something that depends on omega. And you compute the corrections, so you cut off at like lambda order 3, 4, 5, you cut your expression and then you compute the frequency. And this gives you good results, agreement with whatever values we know. But if you try to resum this as omega, what you'll see is that, let's say we look at the omega goes to 0 limit in A, function A is omega flat moduli. You see that A becomes I over 2, right? So in the leading order, this is 0. This is not like, so this is a pole, but we shouldn't too hurry about it. It's not because it's omega on top. So what I'm trying to say is that the first correction here is going to be proportional to omega times lambda, if we just do Taylor. The second instanton is going to be proportional to lambda squared, and the third instanton is going to be proportional to lambda cube over omega, and so on, right? And if you look at the lambda and omega relation, lambda is actually proportional to omega, so every instanton correction here is going to contribute at the same order in omega. So that's why you need to resum infinitely many instantons to get small omega, for example. But it doesn't mean that this answer is incorrect. It does work, but you just need to work with a quantity that's foreign to black hole, which is lambda, it's cutoff. Like black hole doesn't know about this cutoff. I mean, yeah, it knows about the frequency, but it doesn't know about the cutoff. And so that's interesting part of it. And so let's forget about the flat case and move on to like half.
Yes.
You got what's this slide number? We don't have numbers.
Just to be sure, for these for the SADS4 case, the relevant separating curve is for the separating theory, right? F equal to 4.
Yeah.
Which is conformal, so there's no lambda.
Yeah, there's Q. Instead of lambda, you have
Yeah,
to the 2
so
pi
the
r.
marginal Q is different. It's
Yeah, yeah,
dimensionless.
But it doesn't change anything in the equations. It's just you use Q instead of lambda. And the good thing about it is that you can't have expansions. You can't have dimensionless expansions in lambda, but you can have dimensionless expansions in Q.
Yes.
And that's the good thing. That means that we can expand the QNM frequency in some dimensionless parameter. And that's the good thing for SADS. Now we're going to be expanding the QNM frequency in the radius of a black hole or in Q.
Can you explain the parameter on the black hole that corresponds to Q?
Yeah, I mean Q or Q squared or T, we call it. Yeah, it's related to the radius. It's like T.
The Q is complex. You have two.
Yes, proportional. There is like R plus R minus some ratio. I can write to you. Yeah, I have
What about the mass parameters?
Hmm?
The mass parameters?
The mass parameters are they basically one of them, like you can choose them 0, S, minus S, and omega. So one of the masses is omega. And other masses are fixed to integer 0 or minus.
Just for the dictionary to work.
Yeah. But the thing is that here again we want to have analytic expansion in some small parameter, and quantum Zyberg-Witten periods will be not enough for different reasons. But one of the main ones is that the boundary condition is different. When you do the Zyberg-Witten quantum curve, you ask for the wave function solution to be regular at certain points, and it turns out that the ADS boundary is not at the singular, is not situated at the singular point of the equation. So the boundary condition is applied at some random point from the point of view of the equation. This one, we're going to work, first approach, we're going to work with small t. Small t is, this t is exactly like the Q squared. And small t, you see that this is 2. So basically the infinity of the ADS is at 2 in this z variable. And so that's why the wave function is not going to be regular at the point actually z equals 1. So the Zyberg-Witten story asks for the wave function to be regular at z equals 1. We are going to be asking for the wave function to be 0 at z equals 2. And so this immediately means that it's not regular at z equals 1. So, and it should be regular at 1 at the z equals t, which is the horizon. So almost always the boundary condition in our problems are you're asking for regular at the horizon solution. It depends on the wave. It's not like big physical thing because you can change the wave function. It's not going to be regular. But if you, it's easier if you can. It's easier to choose the regular boundary condition for the wave function.
Is there any meaning to the physically relevant boundary condition on the Zyberg-Witten theory side?
This should, I mean, if you don't impose the regularity, you're not getting the period written in terms of Nekrasov-Zhitashvili function, but you can write the full solution with the help of Nekrasov function with, what is it, defects.
That's what I was guessing. So it's
effects.
relevant to the temperature bending function with defect.
With defect, yeah. But again, that's the whole thing, is it's not gonna give you the answer I'm gonna get. By the same reason is that you need to resum a lot of instances because of the certain because of the black hole specific things. And so we're gonna introduce small parameter. In this case, it's gonna be t, but it's a general approach. It can be anything, like we call it kappa, and we're gonna have like two local regions, one around 1 and one around t, two local variables. And in both we're gonna so the wave function is gonna be just perturbatively written like that. And yeah, people do the same things with numerics, but they just don't they don't have the functions there. So like, yeah, we have a first co-author from the first paper. He does, or just we have the same papers, similar papers. He did similar things for the ether, I think, and everything was numerical. So he also has an expansion, but he computes everything numerically. So here we're gonna write the wave function as a perturbative expansion, and the zero order solution or leading order solutions f0 and g0. The main thing is that they are elementary functions. When you, for ADS, they're like polynomials and the logarithms. And this how you can choose the parameter in certain way, or this just happens like that. And so f0 is the one that satisfies the boundary condition in this region. So and g0 is the other one that doesn't satisfy the boundary condition. And then the Wronskian is a rational function always, which is also important. And so this is like the picture where we solve the two regions, like the right region is on the left and left is on the right. It's like, this is because the picture is in z coordinate and not in like zr coordinate, but that is not really relevant. And so we're solving in both regions, and then we're asking for the wave function to be continuous and its derivative to be continuous in the intersection here of two regions somewhere. And obviously this is the complex z-plane, and the actual physical problem lives on the real slice, which is this half circle. So the generic solution in each order is given by this Lagrange variation of constants way. You can write it in this way. So in each order, your contribution is this given by this integral. Their f0 and g0 I already told you, the leading order solutions, and eta k is just depends on all the previous orders. So it's perturbative. And this is basically the recursive thing, right? And ck's you can put to 0. This is just overall normalization of the wave functions. And the constants bk here, you compute them by applying the boundary condition and the continuity condition. So exactly in the ADS case, the small parameter is t, and it is related just to the radius of black hole. So here for small t, we are talking about small black holes. And then we get that in each order, the contributions to the wave function are written in terms of this. All the integrals will be written in terms of this multiple Fourier logarithms. And another definition of multiple Fourier logarithms is that it's just an iterative integral of like forms of poles like this. So like you integrate recursively different poles like 1 over z, 1 over 1 minus z, and you'll get multiple Fourier logarithms. So this is the first set of words that we're gonna have for the ADS case. And the frequency is an expansion of expansion in terms of the RH parameter, and the zero order frequency is obviously this is just a ADS space without anything. That's the known result, and then you have the corrections that are some analytic things here, and since we have the wave function is written in terms of multiple Fourier logarithms, and why is it? One more thing, yes. So you don't have to take integrals anymore, because at each order in the perturbation, in like t to the big K here, everything is going to be written in terms of this functions of order k of weight k or less. So basically, you know, you don't have to take any integrals. You just substitute your nz's, which is written in terms of multiple polar logarithms, and you find all the coefficients. You're happy. You know how, like, up to any order, how the function will look. This is like not a problem. And so the frequencies themselves are now going to be written in terms of Euler sums and MZVs. Initially I will just call them MZVs, but multiple zeta values, they only have one. Like epsilon can be only one for multiple zeta values, but Euler sums they can have plus minus one. So epsilon there is plus minus sum, and there is the whole story about it. People studied it in mathematics, and this multiple polar logarithms business also is studying. Comes up in QCD because they also have iterative integrals there. So this part is had some research done by different areas in mathematics and physics, and your like the some of the first orders here are just not gonna contain any zeta values. They're just gonna be some coefficients like this. So for quantum number L greater or equal to 1 and fundamental frequency, this is just going to always be your first contribution and so on. So this is basically the what we wanted. We wanted analytic formulas, and coefficients are analytically written for each order in perturbation theory. And this, like, we put out the package that does it for you. You just put the quantum numbers, you put what order you want to compute, and this will the software will give you the wave functions and the expansions.
Is the T expansion asymptotic?
That's we think not, but that's a good question to answer. We hope. I mean, our feeling is it not. The thing is, you just it gives you the numeric results. So it gives you compute enough corrections, and you get the digit. You match the computation, the numeric result. So it's at least it's definitely useful in that sense. That gives you the pretty good results. It breaks up in some RH. It doesn't work for every RH. That's why also there is different regimes of black holes. You can small black holes, big black holes. We see that here. If you do for the regime big RH, you need a different set of words, different set of functions. So analytically, they're indeed different, big and small. And so this definitely not going to converge for big RH, but for small RHs, you'll get good results.
Okay, use the the SL2Z transformation to relate it regions.
Yeah, I'm not sure. That's like SLZ transformations. They just do. They don't really relate small and big RH because small and big RH. Big RH is a constant in T. Oh, it's something like 1 because T is a rational function.
So it's like
of
a strongly
RH.
coupled point.
So when you connection between small and big T is not small and big RH. And so next we're gonna also consider this one was Dirichlet boundary condition. So from the point of view of holography or the SFT is not very interesting. It doesn't satisfy the CFT requirements on the boundary. So people like to do Robin boundary condition, and for small parameter now 1 over RH. So for big RH, and this is for scalar sector of gravitational perturbation. So here in the ADS case, before we discussed tensor sector of gravitational perturbations, and this is scalar sector of gravitational perturbations, different equations. And they have 5 regular singularities. At these points, this 1, U1, U2, those are third roots of unity. So you'll see them on the picture. So 1/2 square root of 3 over half complex numbers.
Sorry, so here you're going to change the theory? The corresponding subwritten theory will be the
you cannot solve it anymore. I mean, you can. We didn't solve it in terms of now the dictionary is different. Now I don't know. Like I can't right away answer what is the theory.
I see.
Now
naively, wouldn't you try to use the quiver gauge theory?
Yes, the equations you look for quiver gauge theories, but then what are the parameters? You need to figure this out. Are you gonna you need to find this bigger H regime? Yes. So I don't have these answers. But this approach, this is the second approach with this basically like language of different functions is allows you to just take the equation, and if the leading order is good enough in your perturbation parameter, you can solve it. And so there's now here, remember I mentioned this, like in quantum mechanics, there can be 3 or 2 regions. Here, you can get away with 2 regions, but it's going to be very slow. So we introduce 3 regions here. There is like an explanation behind it, but it's just like, okay, 3 regions I can do way better. Solve the wave function in 3 regions instead of 2 like before. And that's why I have 3 regions. And there's this regular singular points, 1 here, 1 there, 1 here at the horizon, and also 1 next to 0, but we don't write it here. It's negative r, it's unphysical. And so we solve in 3 regions, and again we'll have 2 continuity conditions, 2 boundary conditions. And the interesting thing is that here this is the low-lying mode. So here the question about frequencies was that your frequencies can behave differently, scale differently with your parameter. So this one is a constant when alpha is small, but there is a frequencies. That's why it's a low-lying. Not normal QNM frequency in this case will be scaling with alpha. They will be growing with their age. So the first contribution will be 1 over alpha instead of just constant, probably. We didn't study it yet, but it's just going to be similar. So this is the low-lying mode. It doesn't grow with the radius, black hole radius, and the actually functions that solve this problem are multiple polylogarithms with not just in 1 variable but in several variables, and they define like this. So this is basically the more general case of the previous function, but here the problem is such that all these indices here are 1. So this happens. This happens because you actually have 3 poles at the same distance from 0, and you basically can't choose a region where you only isolate 1 pole. You basically have to have all 3 poles, and then you're integrating with like z minus 1, z minus u1, z minus u2. So your integrals are going to have 3 different poles, and that creates multiple variables, but all of them are constant except for the first. So it's going to be like, this function is going to be like 2, 1, let's say it's going to be z, u1, and so on. And the good thing, there's very good rules about how to take the derivatives. So this is a set of functions, and we know it's very easy how to take the derivative. If you can see here, if you just take the derivative with respect to the first variable, you just reduce s1 by 1. If s1 is 1 and not greater than 1, then you cannot reduce s1 by 1, and this creates 1 over z. So basically, z doesn't matter. If it's 1 here, it's going to be reduce the number of indices. So very easy rule for taking derivatives. And so also people study this because of the hydrodynamics, and the actual they like the M2 brane limit, so that this is they say related to some hydrodynamical problems, and they really compute them, and they have a bunch of rules like for these coefficients here. They should be alternating in certain way because of inelasticity properties. And M1, 2, 3 were known, and it's actually why they're known. They're just written in terms of logarithms of 3, square root of 3, stuff like that. But like 4 and 7 that we are computed, they cannot be written in terms of these things. They will be written like this. So they also have logarithms of 3, square root of 3, pi, but also these things, which are also called colored multiple zeta values. They are colored because those are not just 1 plus minus 1s. Those are those are complex third roots of unity, and so we can compute them like up to 7 here. And yeah, the same website you can find the full expressions and compare it doesn't matter, like people. So for example, we were talking to guys that do that, you say, oh, it will take me couple of weeks to get very good many digits in this seventh or sixth thing, and here you just you can do like whatever. These things like you use Maple knows this better than Mathematica and gives you like up to 40 digits of this constant, and then you can whatever ask for this thing in like up to 15, 20, whatever you want. It's an analytic.
How did people obtain this M1, 2, 3, 4, 4?
There's so I think first paper was one of the first papers, Pofu something.
From field theory?
They
do it from field theory or they do it from gravity?
They just what did they do? I forgot. They computed first two. It's so basically you can use I know like I need to look, I don't remember right off the bat, but I myself have another way of doing it in not using much. Basically you can also it comes down, you can solve just in one region and then look what solution does when you go to another boundary condition, and you'll see that there is like sums like this 1 over n in your answer, which are logarithms. Like they tell you that there was a logarithm somewhere in your solution, and there's coefficient that you need to put to 0. And so if you look at this, you'll figure out first 3. You can figure it out without much this vocabulary and this multiple point logarithms. But if you want to go higher, you actually need those things. They enter the frequency.
But it was a gravity calculation.
Yeah, they were looking at brains and then looking there, and other like also like Japanese we reference, they have like this table where they consider different brains and then compute different things. So and we match with them obviously. But this one is also, so this is the limit. So when you say that RH and L, you take the quantum number angular to the infinity. The same things we do this. They're bigger, but the same. We have analytic answer for this too. So, and finally, this is instead of my what's the time? Okay, nice. So this is instead of like the summary, the future. This everything mixed together, the results and the future things in one thing. And you can notice I added the. This is very important. There is a gradient there. If there is a gradient in the puzzle. Okay, so those we discussed today is just these things, this language of multiple logarithms. When you go back to take the limit to flat case, in something new appears, they will also enter, but you'll need multiple polyexponentials, you can call them. We didn't find much information, but we have enough. We know how to take derivatives. We know for these things. And this one is a bit confusing, but this comes from there is an exponential integral function, right? And you can define it. It's defined such that when the argument goes to infinity, it goes to 0. So this thing doesn't go to 0 when the argument goes to infinity. This thing does, and so you need to have you need to write these functions in terms of this to apply the boundary condition at infinity in the flat case. And so this is a generalization of exponential integral story where they have this.
Sorry, what do these different pieces of puzzle mean?
It's just different languages. Like so, these pieces are for flat case. These pieces are for ADS and DS case, and just it's not too much. There's not too much thought here. It's just pieces, and this is for ADS, but for bigger H for the tensor perturbation and ADS for bigger H. This thing appears. This is a large transcendent, and it's like it's different from the thing by like this. This is it. So for alpha equals 0, this is basically the poly logarithm. But if it's shifted by a non-integer, that's a different function. So we saw this, but yeah, we didn't go too much into detail. So this is just something.
So this one is with Robin boundary conditions.
With Robin boundary conditions, still this.
Oh, for the tensor perturbations.
This is for the tensor perturbations with Dirichlet. But I think it doesn't matter. The boundary condition matters, but not for the type of functions, right? Because we're writing the solution for any boundary.
Right.
So it's up to you what you decide to ask for. But the function appears there is this one. Okay. Thank you very much. And yeah. Thank you.
Sorry, can you remind me, what were the U in your formulas?
This
U1,
U.
U2.
Yeah, sorry. Those are third roots of unity, you know. 1/2. Tell me if I'm wrong.
So, but your formula for the frequency, what is the dependence on masses, etc.? So you scale it out?
Yeah, masses. That's the whole thing. Is that Zyberg-Witten actually the instantons, if you want to expand in these regimes that I'm showing you, are not. You need to resum infinitely many of them to get this strange quantities. And so, but the masses in the dictionary are something like this.
No, I'm not talking about the masses in
Yeah.
Zyberg-Witten, the mass of the black hole.
Yeah. Or the black hole.
That's just scaled out.
Yes. So let's see. In the flat case, it's the radius.
Mhm.
Instead of the mass, we have the radius, right?
But you can write those numerical formulas just because you have one parameter, one dimensional parameter, the radius, right?
Yeah.
Yeah. So most black holes have spin, actually a high spin, right?
Yes.
It could even be maximal. So
It's a Kerr case.
Yeah, they are all Kerr, but even Kerr, almost maximal Kerr. Right?
Extremal, yeah. This
not
is
so extremal. So
the extremal case in Zyberg-Witten is a certain limit NF equals 2.
so you can study that limit.
We already did for the instanton part. We already did the instantons for this. But you can also do what I'm saying is that if you want a small omega expansion and not the lambda expansion, you're gonna have to do something else, and that's what we're working on.
More questions?
Sorry, so the results match what they find in LIGO data?
That's the thing. The LIGO can't really tell you. That's what I was saying. It's the resolution is not enough to see the smaller frequencies, and the LISA should show more. And then, but then like you're not gonna actually probably see the fundamental frequency. They're gonna be overtones. So, but yeah, that's maybe why we also, if you look at and people do that, they look for higher order gravitational correction. So the QNM is linear order gravitational, and then higher order. So back reaction. So basically, looking at the back reaction for the graphs.
But you can match against numerical situations of all of this.
Oh, of course, everything. The numerical is then the numbers and analytics here that we get match. But also you can ask other questions about stability and stuff like that with the analytics.
But is there really an application to LIGO? I mean, LIGO has binary black hole merger simulations. Plus, you can just find most normal modes numerically in various ways.
Yeah.
I mean, what would this add?
This would add to the in a technical way to compute the, if you want to go beyond the linear, right? Study this in more details and go beyond the linear gravitational perturbation. You need to in your equations for the second order gravitational corrections with back reaction, you need to input your wave functions and your solutions.
But you already have fully nonlinear gravitational simulations.
Yeah, but like, I mean, understanding them, well, but still, I mean, that's, yeah, you can put everything into computer and then see, or you can write something analytically and try to, understand a little bit more, but yeah.
So like if you found a deviation from what was expected by the simulations, then I imagine this might be interesting.
Yeah, I mean, simply but it's like studying. Why are we studying QFT if you have the lattice?
Well, it's a bit harder to use in that case, but
You have the lights, just put everything into computer, it's gonna give you the answer. Or
well, let me ask it this way then. I mean, so we don't know. So existence of quasi-normal modes isn't guaranteed, but also the fact that they're a complete set is also not guaranteed. So, right, in other words, they don't form a complete basis for functions. So for something like a black hole merger, you can't necessarily express the time domain signal in terms of quasi-normal modes because there's no guarantee they form a complete basis. So if you really want to describe mergers of objects, you're not guaranteed to be able to do it.
well, that's everything. Yeah, here we're like looking at some regimes, like our solutions to differential equations in some regimes. So, or either a small perturbation on that. I would say for if you want to describe some other phase, you would need to write other not Reggie-Wheeler equations and like other effective equations that describe these other phases of like other more hard parts. And then obviously the linear thing that describes the ring down is not going to describe other phases or more, because they're like they are not a small perturbation like a ring down phase. They're bigger, and so there's need to be a different language for that.
One thing, it's slightly unrelated, but what I found intriguing is that I've heard that there are studies to use the ring down of a merger to study the equations of state of neutron stars when the end result is not a black hole.
Yeah.
So I don't know if any of this will be applicable in that case, because the beauty and the misery of black holes is that they are universal.
Yeah, no hair
Here
theory.
instead you are ready to look at the equation of states. So I don't know if you ever thought about this problem of how to find the equation of state of an object by looking at the ring down. Because I know that people are doing that at LIGO. And
Yeah, that's interesting. I'm just thinking because if your spherical symmetric mass is not a black hole, do you still use the Schwarzschild solution, or
you don't, but you have to match the interior, and then
that's what I'm saying. Yeah, like we are not going into the interior.
I think it's
just as a boundary condition.
Yeah, physically, it's the light ring, which
Yeah.
is at 3/2 the Schwarzschild radius, that gives rise to this ring down. That's an unstable orbit. The imaginary current is the decay of that orbit, and the net light is the frequency. So since the neutron star is larger than that, I don't think these quasi-normal modes have any.
But still, yeah, I mean, this blob will ring down and then settle.
Right.
So,
Yeah. But it'll look very different.
So you cannot use it.
Yeah, I didn't think about it, but it's an interesting question.
So in the ADS case, you looked at two regimes. I understood the large black hole and the small black hole.
Yeah.
So the small black holes are localized in ADS, but in string theory, they would also be localized in other dimensions.
Oh, yeah.
So is there any knowledge of topography of the small black hole results that you have here?
Oh, what? So.
Like you looked at ADS4 or something, ADS4 to 7 or something like that. If you have a black hole which is small in ADS, since the SF is the same size, it would also be localized on S7. So it's probably not valid to have this if you're interested in that.
Well, what we're talking about ADS CFT is like CFT3, right? So, and then it's ADS4, CFT3. People also study that, and yeah, obviously they like for general D, like people that study the holography, they like to have like general D there, right? So you have an equation with a instead of D being 4, for example. I'm not talking about cross S7. I don't know, but for example, you can obviously do like ADS 4, 5, and so on, and they like to expand in this D parameter too. And this could be also possible with like the math, like basically the approach we're selling or whatever we're showing could work there too, but I just need to look at that.
It could work in
More general D, because like it depends how you expand.
but could it work for a black hole in, let's say, ADS5 times S5?
Times I don't know, maybe. I don't know. I need to look at the equations, not like And what is the equation? How is it? In ADS5, definitely yes, people did that, but process 5, I will need to change the equation, and probably the effective potential is going to be different.
That's what would really be cool to move us forward. So, right, I'm just saying, you can't ignore the S5, you can't ignore the compact space in any vectorization I know of, if you're gonna take the black hole to the small. Because it will also be localized in the compact space, so there's lots of KK modes that are important with it.
So you mean the brain that wraps around the S5 is unstable?
But I mean, if you had a black hole in ADS5, which is small, yeah, it would also it would localize itself on the S5. There's no, I don't think there's any situation where it's localized on the ADS5, where it's smaller than the ADS radius on the ADS5, and before the
You mean because of that black brain?
yeah, because it's unstable.
Yeah, I mean, but this is more like this ADS Dirichlet. It's more you can think of it as a good example because it has a lot of properties that are transferable, and it's part of an answer for the flat case. So what I'm doing here is a part of an answer for the flat case. You can take the limit of lambda to 0, and half of the problem will basically stay the same because so why actually another input from the singularities point of view. So this ADS is basically here T. It's like dividing into regions. So, and they're both finite. That's why we have the multiple polylogarithms. The radius of convergence is like they're in a disk of 1. And so this one 0, 2, exactly they cover this disk, and then you can apply the boundary condition at 2 and glue at 0. For the flat case, this goes to infinity. In one of these things goes to infinity, and one singularity stays, one part here stays the same, the other becomes infinite. And merges at infinity, merges with the other singular point, and that creates the exponent. The leading order solution will have an exponent there, so that your functions actually convergent from the singularity to infinity. And it's like there's like z over k factorial to the k, something like this. Obviously like this for the exponential, but I'm saying you add more things here, and this becomes a multiple polar exponential. And so this part stays the same, multiple polar logarithms. This part becomes another function, but when you apply the boundary conditions, it boils down again to multiple zeta values and stuff like that. The function is different, but the frequency is going to be written in terms of the same language, in terms of the same language of MDVs. So in that sense, it's useful to me because I'm thinking about the flat case and that. And also we do bigger H, which is M2 brain, and then it's fine. And the same goes there, because like if you don't, and it's easier because like this is a good example, very simple, one variable, multiple polylogarithms, and then it becomes harder in other regions, but you already have one part of the question answered.
So let's again.